today in class, we talked about dilations and saw what kind of properties they have. So we know dilation is not a rigid motion because it does not preserve length and angle measure. In fact, it only preserves angle measure. The lengths are always going to be proportional to one another. So it's either going to get bigger by the same amount or smaller by the same amount. Now, a little reminder, we talked about K being a scale factor, which is whatever I multiply by to make my shape bigger or smaller. And when I do this multiplication, it's always going to keep the original line, like AB here, parallel to the new line. So we're always going to have parallel lines when we have a dilation. So that being said, when I go and look here at exercise number 1, in the following diagram, we have angle BAC has been dilated with a center of D and a scale factor of 2. So remember what that means. If I was to take D and extend this line through with my compass, this amount and this amount are the same. Just like DA and AA prime would be the same. And the same thing if I continued that through B. So we know those pieces are getting bigger by the same amount. So I also can see that because of that dilation, AC and A prime C prime are parallel. Remember, it's a ray because it has one point and then extends on forever in the other direction. Now I'd also have the original line AB getting bigger by a scale factor of 2, but those rays are parallel as well. Now remember, with these parallel lines, they form two things that should stand out to us. Parallel lines form either congruent alternate interior angles or corresponding angles. So right here, I know that angle 1 and angle 2 are congruent because those are corresponding angles. One's in between the green lines, one's outside, but they're along that same transversal line. And 2 and 3 are also corresponding angles, which means all 3 of these angles have to be equal. Now, if I wanted to verify this, I could take the top part of my compass and see where the protractor is. I would line up my clear piece where that circle dot is right there, line up the edge along AB, and I should get 35 degrees. And if I do that again for angle 3, also 35 degrees. Now, they won't make you do that on the regions, so you don't have to really practice that too much. But what I care more about is that knowing those two are congruent is because of the parallel lines, and we know parallel lines form congruent corresponding angles. Okay, so we talked about this a little bit in the previous lessons, but the real important fact about dilations, besides keeping those lines parallel, means that angle measure is always preserved. So length will not be preserved. That's why it's not a rigid motion. The size changes, but angle measure is always intact. So that being said, if I look through and I have a triangle DEF that's dilated by a scale factor of 5, so it's getting bigger from the original, what must be true? I can automatically cross off 1 and 2 because my angle should never change size. So the angle should always be congruent still. Now I have to remember that the scale factor is saying it's getting bigger. So my original was triangle DEF. That's the one that's being multiplied. So it's like 5 times one of those sides would get me that. So I have to be careful with where the primes are. I have to be choice 3 because EF would be the original. It's got no primes. I can't take E prime F prime and then multiply it by even more. So that number 4 is there to trick us. So we want to make sure we're going with choice 3. Same kind of thing in number 3 though. We have the diagram. It's rotated 180 degrees and then dilated. We get all the sides. What relationship must be true? Automatically cross off 1 and 2. Anytime I see the angles that are not equal, they got to go. And then, like we did in transformations the first time around, I can stack these sides together. So ABC and triangle DEF. So remember, those sides always have to correspond to one another. So if I look, A and C are from this top triangle here, but then A doesn't go to F. So that's not true. But if I look at the next one, BE and CF, that is going to be true. So it's going to be choice 4 here. Now if I go to the next page here and kind of keep going a little further with this with exercise 3, diagram below we have E prime F prime G is the image of EFG after a dilation of an unknown scale factor with a center point. Using the properties of dilation, what must be true about the angles of both of them? They're congruent, right? So I should know that angle E is congruent to angle E prime. Angle F is congruent to angle F prime, and angle G is congruent to angle G prime. When you're trying to find the center of our dilation, we know it's not any of these pieces. It's not E, F, or G because all three of them have a new location. If the center was one of them, it would not move. We saw that on lesson 1. But all you have to do is take your straight edge and from F to F prime, extend down. Now, I know that E prime, F prime, G prime got bigger, so I extended down in this direction. I'm going to do the same thing from G to G prime. This intersection point is enough to tell me that that is point D, my center of rotation, of dilation. I could verify that third point and do E to E prime, and it would pass through as well. I don't need to. I only need 2 to make this happen, so the third one's just extra. But now that I have this picture set up, we're going to set up something we know. So with that being said, I have DF is 4, and the whole thing, D to F prime is 6, DG is 3, and D to G prime is 4.5. We want to calculate the scale factor to the nearest tenth. So anytime we're going to find scale factor, remember, it is new over the original. So what we can do here is we can look at the primes. E prime, F prime, and G prime are bigger than E, F, and G. So in this case, I know it's going to be big over small to make this scale factor. And when I take one of the sides, I'm going to take 6 over 4. And we get to the nearest tenth, 1.5. If I did that for the other 2 sides as well, 4.5 over 3, still getting 1.5. Okay. So that being said, really, a scale factor always shows us what we could multiply by to get the new picture. We can also do that by setting up proportions because you're taking the big over the small. So let's see that in exercise 4. So when I'm looking here, I have ABC. We have D and E have been located so that DE is parallel to BC. We want to give a dilation that will map BC onto DE now. Just like we were specific before, BC to DE, notice it's getting smaller. So when I talk about my dilation, I want to be sure to talk about 2 important things. This dilation is centered at the one point that doesn't move, so it's going to be at A. So if I think that line is kind of going along that path, and it's going to have a scale factor, remember it's new over original, so if I want to be on DE, it's going to be DE over BC. And that's how I'd be specific about that transformation. This is what's known as a similarity transformation because it's not going to necessarily make congruent shapes between the two, but it keeps the shapes similar, and we'll talk more about that later. In triangle ABC, if it was transformed, why would it now be congruent? Well, we're mapping BC onto DE, right? So just one possible way to show is that we would know B prime, C prime is congruent to DE. So that would be the new one here on this line. And remember, end angle measure is preserved. So you can really use any combination. Like we can see angle side angle or angle side, but we have that one side in there that shows that they have to be congruent. Now the last piece of this is if we go and plot these points on here. So if I have AD is 10, AB, the whole thing, is 15, BC is 12, and AE is 14. And we want to go find the other two pieces. So let's call DEX and ACY. So first thing I should notice is that all these sides have to be in the same proportion. So they all have the same scale factor. So with that same scale factor, I'm going to take, let's say, 15 over 10. Because those are the pieces that I know for sure. If I went to find 12, 12 is part of the bigger triangle, just like the 15 was. So I'm going to put the 12 on top. And x is part of the smaller piece like the 10 was, and now I can just cross multiply. So we would get 15x equals 180. 120. And when I divide both sides by 15, I'm going to get 8. So I know 8 for this side. That same thought process when we do it, I'm still going to keep the 15 over 10. But when I go to find y is part of the bigger side, like the 15 was. And it's going to be over the smaller size of 14. So I'm going to get 10y equal to 15 times 14, which is 210, which means y is equal to 21. So scale factors always keep things in proportion. We could have multiplied those pieces, or we could just set up a proportion, which is usually a little bit nicer. Last idea in this question, exercise 5, it's a former Regents question. So when I read through it here, it tells me that the image of a triangle ABC is after a dilation with a scale factor k. That means I don't know what size it is. Even though it looks like it's double, I can't suggest that I know the scale factor, so I automatically cross off 1 and I cross off 3. Because I don't know that that's the midpoint. I can't really say any of that for sure. The other thing I can't say is that AD is perpendicular to DE, because we don't know that. There's nothing that says it. Even if it looks the part, we can't assume it. But because dilation preserves angle measure like we saw, we do know that BC is parallel to DE. Okay, thanks for watching.